And first we will have Pazit Haim-Kislev who will tell us about symplectic capacity.
So thank you all for coming. As I want to talk about symplectic geometry today, so let me start by explaining a little bit about Hamiltonian dynamics, which is the origin of symplectic geometry. And it is essentially a way to formalize classical mechanics in the phase space. So we consider Q and P vectors of the position and momentum, and H Hamiltonian function, which represent the energy of each state in the system. And then Hamilton equations describe the dynamics and the evolution of the system throughout time. And key feature of this system is that it's volume preserving, meaning if we take some set and we look at the Hamiltonian flow of the set over time, it stays with the same volume. And as it turns out, something even finer is being preserved, this two form, which we denote by omega naught, and it is called today the standard symplectic form. And as it turns out, the Hamiltonian flows which preserve this omega are exactly all the flows which preserve omega. And so symplectic geometry is the study of maps which preserve omega naught, and one can extend this story into a general setting, meaning to all even-dimensional manifolds, which we equip with some non-degenerate two form. And property of symplectic manifold is that they are all locally the same, and they are all locally like the R2N case that we just discussed. And for some time, it was unclear whether one can distinguish between two symplectic manifolds in a way which is different from their topology or their volume, because locally they are the same. And this was answered by Gromov only in 1995, where he showed his non-squeezing theorem, which states that a ball can be symplectically embedded into a cylinder if and only if its radius is smaller. So very, very different from volume preserving state. So this implies that while a symplectic manifold doesn't possess anything unique locally, it still have some global invariants which distinguish it from other symplectic manifolds. And this is essentially symplectic capacities, which will be the focus of this talk. So the non-squeezing give rise to two symplectic capacities, the Gromov width and the cylindrical capacity. So they one is asking what is the biggest ball one can embed into a domain, and one asks what is the smallest cylinder we can embed our domain into. And already the non-squeezing tells us that these are non-trivial quantities. And one can extend this to any function which gives a value to a set, which satisfy these axioms. So in general, we want to think about symplectic capacities as a size of a set, something which represents the size. And so we want it to be behaving nicely with respect to inclusion, smaller if it can be embedded in, nicely with respect to rescaling. And as we don't want it to be the volume, then we want to normalize it in such a way that the capacity of the ball and the cylinder of the same radius would be equal. And from simply the monotonicity, one has that these two capacities are the smallest one and the largest one. And thanks to their introduction, many other capacities were constructed in using very different tools in symplectic geometry. So they're not just these embedding ones like the Gromov width and the cylindrical. And this allows you to study symplectic manifolds using different tools. And so while symplectic capacities are fun, their main problem is that they are very hard to compute. So for a general manifold, we don't know how to compute most of its capacities, and there's still a lot of unknown.
That's the question.
Yeah, sure.
What's so special about the ball in the cylinder? Or those give us the main one.
Yeah, so
The answer is too complicated, you could just ignore it.
yeah, there's nothing special in the sense that the base of the cylinder could be whatever you want, because you just choose it to be because any area preserving method, the base would be symplectic. You take it to be as like Cn. If you look at the Cn, it's like C times Cn minus 1. So in that sense, there is nothing special about it. And yeah, the ball, I'm not sure to say specifically. Okay, so we know what symplectic capacities are, and now we turn to some specific case. So the case of when we restrict ourselves to the R2N case and to convex subset of R2N. And it turns out that this case is special because many of the capacity are known to be equal on this case. And moreover, they are equal to the minimal action over all closed characteristic on the boundary. So what does these words mean? So by closed characteristic, I mean the periodic loop on the boundary of the domain, which is created by the Hamiltonian flow H, such that the convex domain is a subset of this Hamiltonian. And so we have a convex Hamiltonian, and we look at sublevel sets of it, and the Hamiltonian periodic orbits of it are what we try to investigate. And the action of a loop would be the symplectic area of a disk enclosed by this loop. And so even though this is somewhat of a simpler specific case, it's still very hard, and there is a lot unknown. So one of the questions in this would be whether there are actually only one symplectic capacities on convex domains. Specifically, that the minimal capacity and the largest capacity coincide. And I guess the motivation to this was the fact that we know that many of them do coincide in this case. And a slightly weaker version of this would say that the domain with the largest capacity when we fix the volume is the Euclidean ball. So this is a kind of an isoparametric inequality, because we are fixing scaling of the domain and ask who has the largest capacity among them. This is known as the Viterbo conjecture, and it is weaker than the first one because it holds in a trivial way for the smallest capacity, because the smallest capacity asks what is the largest ball one can embed into the domain. So obviously the answer for that is the ball. These days, the spheres conjecture is known as the strong conjecture. Let me draw your attention to the fact that there is something a little bit strange here. Essentially, the use of the word convex. Convexity is not a symplectic property, and it is not preserved under symplectic maps. And in general, if you give me some domain, it is very hard to say whether it has a symplectic image which is convex. So it is weird that we are expecting different behavior on the class of convex domains. And yet, this seems to be the right settings, because it is not true Hölder's conjecture for starship domain, and they hold up to universal constant when we are restricted to convex. Moreover, since the conjecture was made, it was proven in many specific subclasses of convex domains. And one last remark is that it was shown that the Viterbo conjecture for a very specific case is actually equivalent to the famous Mahler conjecture from convex geometry, which is now been open for over 80 years. So what seem like a natural, simple question might not be this easy. So let me now move on to some of the approaches to try and study this conjecture. So as we said, they are very hard to compute, so let's try ways to compute it better. So recall that we are interested in Hamiltonian periodic orbits with minimal action. And Clark's tells us that there is some variation principle we can use that makes those loop in correspondence to taking the minimum over a functional, but this would be over an infinite loop space. So it's still difficult. And a few years ago, I showed that when we are talking about a polytope, one can do some action decreasing rearrangements such that now the minimum we take of the functional is over some finite dimensional space. And now taking this reduced number of options and setting it into the possible actions one can get, we get a combinatorial formula for the capacity of convex polytopes, which was kind of the first time we could actually calculate the capacity of general domains. So this was like nice and very helpful in improving the intuition one has about capacities. And very naturally, one tries to find counterexamples for the conjecture. And one fails. Couldn't find counterexamples using blind search. There's using this formula, and moreover, many of the attempts converged to the maximal value, the conjectured value of the conjecture. So that gave us some sort of positive belief in the correctness of the conjecture. Let me say a few words about also the dynamical properties one would expect from the convex domain. And mainly if we are trying to imagine what dynamical property maximal of the capacity should have, then it makes sense that it would be optimizer all over the boundary of the convex domain. Mainly, we call it symplectic soul, and we say that every point on the boundary is a part of a closed characteristic with minimal action. So it's very natural to expect the maximum of the capacity to satisfy this. And the ball does satisfy this condition as it's foliated by Hopf vibrations, which are closed characteristic. And it was really shown that symplectic sols are local maximizers of the capacity, and in R4, they are actually symplectomorphic to the ball. So this is again some evidence in favor. Another approach, as I was saying, is that convexity is strange because it's not a symplectic property, would be to try and think what is the intrinsic symplectic property or dynamic property that a convex domain satisfy that cause convex domains to behave in a different way. And an attempt for that is called the dynamically convex. And it was hoped or thought that perhaps all dynamically convex domains are symplectomorphic to convex. But then it was shown that they're constructed in a convex domain example, which it does not satisfy Viterbo, which means that either Viterbo conjecture doesn't hold, or dynamically convex are not necessarily symplectomorphic to convex. But then it was shown that one can construct dynamically convex examples which are not convex. So again, we are enforcing our belief in Viterbo conjecture. So now that you are thoroughly convinced that the conjecture is true, I can tell you that very recently constructed a counterexample to the conjecture together with Iran. And it's surprisingly simple example, which is the regular pentagon, Lagrangian product with a rotation of the regular pentagon by 90 degrees. And
again, what is it? Can you just repeat? I did not
Yeah,
understand.
The counterexample is a Lagrangian product of two regular pentagons. One is rotated by 90 degrees from the first one. Okay, this is in our four. And one can calculate the minimal action over such an example and see that it's have larger capacities than the ball. And as a consequence, it also says that the minimal action does not coincide with the smallest capacity. So not all capacities coincide. But he also remarks that one can generalize this to higher dimension as well. So it's in every dimension.
Maximal capacity for which it fills?
Hmm?
Which capacity does this fill?
So the minimal action one, the one that all capacities coincide on for convex. And somehow, instead of answering questions and resolving the conjecture, it feels that it gives us a lot more questions instead, such as we had a very natural dynamical property suggested for the maximal of the capacity dissolve, but now we don't have even a guess what should be the property of dynamical properties of the maximum of the capacity. Again, due to the amount of evidence in favor of the conjecture, one would expect that there should be some natural subclass of convex domains for which the conjecture still holds. And for instance, if they still hold for centrally symmetric domains, it would still imply the Mahler conjecture. So it's of great interest. And again, trying to understand what are sort of the dynamical ways to try and define convex in a more natural way from a symplectic point of view. And kind of the fact that Viterbo doesn't hold for convex sort of reopens this question, how really different dynamically convex and convex are. But there are many more questions, but let me finish.
We have time for a quick question.
So why, maybe convex has nothing to do with the symplectic. That was the thing you started with. So why are you, I mean, it doesn't, isn't this a lesson for what you talk about?
Right, there still seem to be very different behavior for, say, star-shaped domain, because the conjecture doesn't hold at all for that. They can go to infinity, they're not bound at all. I agree that if you can find some other dynamical properties that one can say that if you satisfy this, you behave in a different way. It's not, doesn't have to be necessarily all convex domains, or might be a bigger class than just convex domains. That would be probably a good answer for this conjecture.
Just find the class for which the conjecture
Yeah,
is true. for
natural
the
one
domain.
from a symplectic definitions.
Okay, let's thank Pazit again.